Welcome to The Explainer. Today we're taking a deep dive into the heart of Java programming, but I actually want you to think about it a little differently. Imagine your Java code as a massive, bustling city road system. Just like a real city, we have to direct traffic efficiently, make sure vehicles take the absolute right paths, and crucially, handle those inevitable accidents without shutting down the entire grid.
Which brings us to a pretty fundamental question. How does a program actually make a decision? Because, let's be real, code that just runs in a straight, single-lane line from top to bottom, it's pretty useless on its own. Without the ability to evaluate conditions and make choices, software just can't react to user input, it can't process data dynamically, or, well, do much of anything interesting. We need intersections, we need traffic lights.
So, here is our roadmap for today. 1. Directing Java traffic. 2. The switch statement. 3. Handling code exceptions. And 4. Try, catch, and finally.
Okay, let's dive right into Section 1, Directing Java Traffic. Let's start with single selection statements, which form the absolute baseline of how we alter the flow of our execution.
Now, this is the visual heartbeat of a program making a decision. It's the Boolean logic of an if statement. When the program reaches that diamond shape, our logical expression, it basically pauses to ask a question. If the value evaluates to true, boom, the traffic is routed to execute a specific action statement. But if it evaluates to false, the code simply bypasses that statement entirely. It's the ultimate fork in the road.
But how do we physically form that logical expression inside that diamond? Well, we use relational operators. Think of these as the literal decision makers formulating our conditions. They figure out if a specific relationship exists between two values. Is one value greater than another? Are they exactly equal or maybe not equal? We can even stack these together using logical operators like and, or, and not to build some seriously complex rules. Using these operators is exactly how we give our program the actual rules of the road.
The really crucial takeaway here is that this single selection statement executes code only if the condition is true. For instance, say you want to stop a program because a user accidentally entered a negative number. The condition checks if the number is less than 0. If true, the stop sequence initiates. If false, it just carries on. And if we want to provide a specific alternative route for when it's false, we simply tack on an else block. That instantly turns our single fork into a clear two-way street.
And looking at the physical pathways on a circuit board is a really great reminder that these software decisions aren't just theoretical. Ultimately, these control structures are routing actual physical electrical traffic through the hardware of the machine. The elegance of the code you write directly translates to the physical efficiency of the computer itself. It's pretty wild to think about.
All right, Section 2, the switch statement. So what happens when you have a situation with 4 or 5 or even 10 different valid routes?
If you're testing a variable against a bunch of specific, discrete values, chaining together a dozen clunky sequential if or if-else if statements is going to make your code incredibly difficult to read and maintain. Nobody wants to sift through that. Instead, Java gives us a multi-lane intersection, the switch statement. It lets us handle all those discrete paths elegantly within a single, highly readable structure.
Let's break down the exact mechanics of this multi-lane interception. First off, the switch statement tests a specific variable. Then, it routes the execution straight to a matching case. But pay attention to the vital traffic signals here. The break keyword tells the program to exit the intersection entirely the moment a match is executed. Without it, the code would just keep bleeding over into the next lanes. And that default keyword? That is our safety net. It ensures that if a driver takes a route that straight up doesn't exist, we can gracefully let them know they made an invalid choice.
I want you to mentally test this out with me for a second. Imagine a scenario where we actually evaluate an expression right at the intersection. If we have a switch statement testing the expression number plus 2 and our input number is 0, what happens? Well, the evaluated expression becomes 2, meaning the program just bypasses case 1 entirely and routes perfectly right into case 2. This dynamic evaluation gives us an incredible amount of flexibility.
Taking a step back, this idea of global data traffic really captures what we've been building. Between our conditional statements and our switch statements, we have total, absolute control over the flow of our program's execution, no matter how complex the routing gets. But there's a pretty glaring vulnerability here. We've planned for all the expected traffic. But what about the unexpected?
Which leads us to Section 3, Handling Code Exceptions. Because seriously, what happens if an error suddenly breaks the program?
We are officially shifting gears into exception handling. It is time to build the ultimate safety net for our code.
In the real world, programs do not run in a perfect, pristine vacuum. They have to interact with unpredictable users, failing network connections, missing files, or users who inexplicably decide to type the word banana when you ask them for a phone number.
And here is the core problem. Without exception handling, an unexpected event like that triggers a total coding catastrophe. The program just terminates entirely and spits out a massive, ugly red error message to the console. From a user experience standpoint, that's a total failure. It ruins whatever the user was trying to do, and it causes huge headaches for developers.
I love this guiding philosophy from the source text. When an exception occurs, it should perform appropriate action. Our goal here isn't just to acknowledge that a failure happened. Our goal is to catch the error, execute a graceful recovery, and ideally allow the program's execution to safely resume. We are looking for a detour, not a dead end.
Moving on to Section 4, Try, Catch, and Finally. Let's look closely at the mechanical steps of these blocks and see how our emergency response system actually operates.
Okay, here's the exact step-by-step sequence of events when an accident happens in our code. First, the program attempts to execute the code inside the try block. Makes sense, right? Now, if an exception is thrown, any remaining statements in that try block are immediately ignored. The program wisely stops trying to drive off a broken bridge. Next, it searches for a catch block to handle the mess. And finally, a finally block will execute to wrap the whole thing up.
But the really critical part is how Java finds the correct detour. When that exception is thrown, Java searches the catch blocks in the exact order they appear. It's literally hunting for a match. If the type of the thrown exception matches the parameter type defined in one of the catch blocks, then that specific chunk of code executes. That means you can create totally different emergency responses for different emergencies. You could have one tailored response for a missing file and a completely different detour for a math error. And then there's the finally block. Think of this as your ultimate cleanup crew. It executes regardless of whether an exception occurs or not. Even if the try block runs flawlessly, or even if the catch block successfully handles a totally catastrophic error, the finally block is guaranteed to run at the very end. It's absolutely essential for doing things like closing data connections or releasing memory so that no resources are left hanging in limbo.
Think of exception handling like a satellite communication system. It's the ultimate automated dispatch center for our traffic grid. If atmospheric interference disrupts the signal, which represents our exception, the satellite doesn't just completely shut down and drop out of orbit. No, it catches the error, automatically recalibrates its signal using emergency protocols, and reroutes its data stream to make sure the connection isn't lost. That exact level of resilience is what try, catch, and finally blocks bring to your software.
By mastering logical conditions, utilizing robust switch statements for complex routing, and wrapping your most vulnerable code inside a powerful exception-handling safety net, you really transform from someone who just writes lines of code into an architect of truly resilient software. So I'm going to leave you with this thought. Are you ready to take total control of your code's journey? Thanks for joining me on this explainer, and happy coding.